first year to David Marr. I'm sure had a timely death. And Don got his PhD in 1983 in computational vision. We snapped him right up here, and he's been a colleague for 20 years. He's won several awards, a Distinguished Science Award from the APA and the Trollin Research Award from the National Academy of Sciences, and a teaching award here at UCI. And I think perhaps his major work is observomechanics, and I think he'll tell us a little bit about that book he did with Bruce Bennett and Jitin Prakash. I've enjoyed being a colleague of Don for many, many years. I know he's a very gentle soul. If you happen to bump into him in the hall, he looks at you and says, "No matter." In any event, his talk today is for Physics from Consciousness.
Thank you, Bill. I have an ambitious plan for the talk. I first will argue that there are good reasons to think that consciousness is fundamental in science. I'll then try to give mathematically precise definitions of what I'll call conscious observers and conscious agents. I'll then introduce several fundamental postulates that I think are helpful if we're going to try to have a science that takes consciousness as primary. And then I'll actually develop a dynamics of these agents in 1, 2, and 3 dimensions, look at some of their properties briefly. And then, to try to tie the consciousness model into standard physics, I will look at group theory and symmetries that are shared between the two. And from that, I'll show how you can get relativistic spin-half particles out of the dynamics of conscious agents that I'll develop. And then at the end, speculate about how this could tie into theories of quantum gravity, discrete space-time. So it's a fairly ambitious project for 50 minutes. So maybe questions limited to points of clarification, and then we'll do more deep discussion at the end. Unless there's something too egregious to let go. So, as I mentioned in my last talk, about a year ago, Science had a special issue in which they looked at the top 125 open questions in science. Number 1 is, what is the universe made of? And number 2 is, what is the biological basis of consciousness? And these are related. And what's remarkable is, although hundreds of researchers are now studying the biological basis of consciousness right now, and it's a major scientific topic involving some of the brightest brains in neuroscience and cognitive science, we, as yet, do not have a single scientific theory. There's not one remotely plausible scientific theory about how the brain or some aspect of physics could cause or be our conscious experiences. And this is quite a shocking state of affairs. The question is not a new question. It's been around since at least the time of Plato. And it's striking that we don't have a single remotely plausible scientific theory. The situation is summarized by Colin McGinn, a professor in England. In the journal Mind, he recently wrote, "We know that brains are the de facto causal basis of consciousness, but we have, it seems, no understanding whatever of how this can be so." And this seems to be the state of affairs. Now, there are several reactions to the state of affairs. I think most people in the field say, well, we just need to work a little longer and harder. We haven't had the good idea yet, but if we do more neuroscience research, we'll get the good idea that we need to break this problem. Others, like Colin McGinn, say, you know, we've tried that, and we have pretty good evidence that we're not going to get the good idea. We just can't do this problem this way. It's not that brains don't cause consciousness. It's not that. It's not that brains don't cause consciousness. It's rather that brains do cause consciousness. We're not smart enough to figure out how. We've been shortchanged by evolution in the conceptual department. We don't have the concepts needed to solve this problem. So what we need is not harder research. We need a mutation. And until we get that mutation, we're not going to solve this problem. Okay? I'm going to take a different point of view. I'm going to suggest that the reason we've made no progress is that although physicalism, an ontology of physicalism, has been fantastic in the sciences since Newton. It's done a lot of good work for us. It's run up against a fundamental limitation in what it can do. And my proposal is that we're going to have to fundamentally change the ontology that we do physics in, and science more generally, to handle the problem of consciousness. So my first postulate is that all that exists is consciousness and its contents. And so the mind-body problem, if you have a physicalist ontology, is the standard problem, namely how do you describe how consciousness arises from or is identical to certain types of physical systems. That's the standard mind-body problem, and that's the problem that I just have indicated we literally have nothing intelligent yet to say about. So I have a different problem. I'll call my view conscious realism, the view that consciousness is fundamental. And the conscious realist mind-body problem is to describe precisely how consciousness, I'll call them conscious agents in a moment, conscious agents construct physical objects and their properties. So the idea is the mind-body problem is the problem of how is consciousness related to the physical world. Most people say, let's start with the physical world and try to get consciousness. We've made no progress. So I'm saying let's start with consciousness and try to get the physical world. And one way to think about this, I mean, it's a strange and out there, out of the box kind of idea, but think of it in terms of search strategies for the field. 99% of the researchers in the field are in one part of the search space. We're all assuming physicalism is true, trying to figure out how brains and physics more generally causes consciousness. 99% of their efforts there, but the search space is very, very big. And included in that search space is the hypothesis that maybe consciousness is fundamental and we need to get physics from consciousness. At least a couple percentage of us need to work on that part of the search space. So in that spirit, maybe this won't seem quite as implausible an approach. So let me give an example of what I mean first by a conscious observer. And I'll use as a concrete example the perception of structure from motion. If I just show you some static dots, you see the dots lying in a plane. But if I put them in a special kind of motion, you create a brand new dimension of experience, literally a new dimension of experience. You create a third dimension of depth and a rigid object, namely a cylinder, that you see rotating back and forth. So here's a concrete example of perception in action, and in particular conscious experience in action. So here your conscious experience is of dots in 2 dimensions. Here your conscious experience is of something in 3 dimensions moving rigidly. And that's the aspect of consciousness I'm interested in here. Not self-consciousness or very high-level kinds of consciousness, just raw sensory experiences, something that a rat might have. That's the level I'm interested in. Now, so here the input is some 2D motions of dots. Your conscious output is a 3D cylinder in rigid motion. And in computational vision, Shimon Ullman proved a theorem that if you have 3 views of 4 points, in other words, 3 videotape frames, and each has at least 4 points, you can mathematically account for our perceptions here. So here's his theorem. Given 3 orthographic projections of 4 non-coplanar points, the 3 views almost surely have no rigid interpretations. That means if I just throw down 4 points at random in 3 frames, the probability that you can actually give a rigid interpretation is 0. And that's what you want. You don't want to have every stimulus that you get trigger you to give a rigid interpretation. You want it to be a very special event that the stimulus in front of you is compatible with rigid interpretation. However, some 3 views of 4 points do have rigid interpretations. And if they do, then generically they have precisely 2. And the 2 are mirror images of each other. That's Ullman's theorem. And if we just look abstractly at the structure of Ullman's theorem, it's as follows. Y is the set of all possible 3 views of 4 points. So it's the set of all possible displays I could show to you that have 3 views of 4 points. So Y is the set of all 3 sets of 4 points in R2, so it's actually R24. X is the set of all possible 3D interpretations that you could conceivably give, rigid or not. And so X is the set of all 3 sets of 4 points in R3, which is R36. There's a special subset of Y, a set of displays that will actually be compatible with the rigid interpretation. So that's the set S, displays with a rigid interpretation. And I've drawn it as a curve here. It's going to be very rare, so it's a measure zero set, and I've drawn it as a curve within Y to show that. Up here, I've drawn E to indicate the rigid 3D interpretations. And P is the orthographic projection relationship between X and Y that basically strips off the depth coordinates. And then there's a mathematical object Q, which is a Markovian kernel, which for every display, so each point of S corresponds to a full display that triggers you to see a rigid object. And since, according to Ullmann's theorem, for each display there are two rigid interpretations, what Q will do is for every point of S, it will assign a probability measure that's supported on 2 points up here on E. It'll give you two rigid interpretations. And the mathematical object which does that is a Markovian kernel. Okay. So that's the mathematical structure of Ullmann's structure for motion observer. And this will be the foundation that gives you a concrete example of what I'll generalize now to just the abstract notion of a conscious observer in general. Okay. So conscious observer, oops. So now Y, instead of being R24 as in Ullmann's case, I'm just letting Y be any measurable space. X is any measurable space, E is any measurable set, so is S, P is any measurable function, and Q is any Markovian kernel. So this mathematical structure, which we saw a concrete example of in Ullmann's case, is what I'll call a mathematical definition of a conscious observer. The points of Y represent the conscious sensory inputs to this observer, and the points of E are the potential conscious experiences that this observer creates in reaction to receiving these conscious experiences here. So we propose the observer thesis that every synchronic, that is static, perceptual capacity, regardless of modality, can be described as an instance of a conscious observer. So we're claiming this mathematical formalism that I just presented is completely universal. Every perceptual capacity can be represented as a conscious observer. The status of this thesis is much like the Church-Turing thesis in computation, right? So Church-Turing thesis says that every algorithm, every effective procedure can be represented as an instance of a formalism called a Turing machine. That's the same kind of proposal we're making here. Both theses are empirical theses. You could disprove the Church-Turing hypothesis by showing an algorithm that can't be represented as a Turing machine. No one's done it. I don't think anybody's going to do it, but it's at least in principle doable, possible. The same thing here. We're claiming this is an empirical thesis. We're claiming that you'll not find any perceptual capacity, human or non-human, that cannot be described as an instance of this conscious observer formalism. And what this formalism says is that a fundamental property of consciousness, the fundamental act of consciousness, is to create new conscious experiences. And why do I say that? Well, if I go to this display again, you start with conscious observer is given conscious experiences of this type, namely two-dimensional dots. What it produces has an entirely new dimension of experience, literally. You see depth where there wasn't any depth before. You see a rigid object where there wasn't a rigid object before. You are de novo creating a new conscious experience. And so that's what this structure is saying. You start off with a less rich set of conscious experiences. You end up with a new, richer set of conscious experiences that are not at all reducible in any way to the original experiences. So the fundamental act of consciousness is this creative step. So this formal structure, of course, doesn't do the creation. It's just a model of that creative aspect of consciousness. Okay. So this is, I'll call this what we just said, our second postulate, namely that conscious observers create de novo new experiences. That's the fundamental act of consciousness. Okay. And the definition of conscious observer is the mathematical model of this postulate. Now, conscious observers won't be the star of the show. The star of the show will be conscious agents, and conscious observers will just be points of the state space of the dynamics of conscious agents. But we'll come to that in a moment. There is the question of how do conscious observers relate to the physical world? And how does consciousness relate to the physical world? Now, there's two levels that we can think about. There's the microscopic and the macroscopic. And I'll just deal briefly with the macroscopic and leave it aside so we can focus on the microscopic. At the macroscopic level, you can ask the question, how far have we advanced in a theory that starts with consciousness and gives us the macroscopic, the everyday physical world? And I'll claim that we're very far along on that process. All of the research that's been done, for example, in computational vision, in which researchers claim that they have discovered principles by which human vision reconstructs the shapes, the objects, the colors, the motions, and the shapes of the depths and so forth of all the objects out there. We can reinterpret all of that literature and say that those mathematical models aren't models of how we reconstruct the physical properties of a pre-existing world. They're instead models about how conscious observers de novo create the objects, colors, motions, and shapes that didn't exist prior. Now that sounds like a stronger thesis, but in fact it's a weaker thesis than the reconstruction. Reconstruction hypothesis about vision says there is a physical world out there that exists independent of us. It has objects in 3D with colors and motions and shapes. That's what's really out there, and our perception reconstructs those properties. My hypothesis is actually more conservative. I say we certainly do construct objects, colors, motions, and shapes, and I will leave open what's really out there independent of me. That's more than I know. It's certainly more than I know to say that what's out there perfectly resembles what I'm experiencing. In fact, the chances of that being true on evolutionary grounds is quite low. What I'll propose instead is everything that we experience around us, the 3D world of objects, colors, and motions, is not a faithful depiction of what's really out there independent of us in a physical world. Rather, what we have is a dumbed-down, species-specific user interface, like the user interface on your computer screen. The point of a user interface is to make things very, very simple. This thesis, this is from the talk last time, this thesis folder may be rectangular and blue and in the lower right-hand corner of the screen. That doesn't mean the file itself is rectangular or blue or in the lower right-hand corner of your computer. There's no resemblance between the symbols and what they represent. No resemblance whatsoever. And it's precisely because there's no resemblance that they're useful. This is contrary to the way we think of perception usually. Most people, most textbooks in perception say, for perception to be useful, it must resemble whatever it's representing. Nonsense. It works best if it doesn't resemble, if it in fact dumbs down and simplifies things so that a particular species, namely Homo sapiens, can survive in its niche. That's the point. So, and this is something that Pinker points out in his book, How the Mind Works. He points out on evolutionary grounds, we're organisms, not angels. Our minds are organs, not pipelines to the truth. Our minds evolved by natural selection to solve problems that were life and death matters to our ancestors, not to commune with correctness. So if you take evolutionary hypotheses quite seriously, then there's very little reason to take our perceptions as actually resembling whatever happens to be out there. Now, I'm not claiming there's nothing out there. I'm not a solipsist that says there's nothing out there independent of me. There is something out there. But we should be open to many different theories about what it is. The theory that what's out there is very similar or resembles what we perceive is one theory, and one that's very unlikely. I mean, the chances of that are very, very low. On evolutionary grounds would be incredible. It would be like winning the lottery if we were the species that got it right. So that's all I'll say for now. We can come back to it if you want. That's all I'll say about macroscopic objects and macroscopic physical world and conscious agents. I now want to move on to dynamics. The conscious observer is a static entity. It's for observation at a particular moment. But now I want to talk about agents in a dynamical conscious situation. So here's my third postulate, the action postulate, that conscious agents move on a state space of conscious observers. So, a couple key points. This is not a dynamics that's taking place in space and time. Space and time are, in the framework I'm proposing, space and time are not fundamental. Space and time are stupid symbols that Homo sapiens comes up with to get through the day. They're part of our species-specific user interface and have no deeper significance than that. So space and time are Homo sapiens-specific symbols and nothing deeper. So the state space in which conscious agents are moving is not space and time. The state space, each point of the state space is that full structure I showed you, namely a conscious observer. Okay? So effectively, what a conscious agent is, mathematically, it's a Markovian kernel on a state space, each point of which is a conscious observer. That's technically what's going on. Intuitively, what that means is, as the agent changes points in the state space, is changing how it creates its conscious experiences, new ways of creating conscious experiences. And then I want to connect this science of consciousness to physics. And so I have to have certain postulates. The key postulate will be that physics, in particular, microphysics, quantum physics, and so forth, represents stabilities, symmetries of the dynamics of conscious agents. So what our game will be is to write down dynamical systems of conscious agents, look at the symmetries of the dynamics, look at the symmetry groups, and use those symmetry groups to match to the symmetry groups in physics, and make the connection at the group theoretical level. So physics is limited in the aspects of reality it can see. It can't see the conscious agents themselves. It can only see the stable dynamics of the conscious agents. So I'm also proposing a limit to physics and why physics can't help us solve the mind-body problem in its current state. So, to be specific, let's start off in, oh yes?
You keep mentioning dynamics. No one talks about dynamics for some time period.
That's right.
Is that supposed to be related to our conscious concept of time?
It's, so the notion, good question, the notion of time will be a species-specific user interface variable, and the notion of sequence that we'll have here will not be stuck in like a space-time notion of time. It will be a separate notion of sequence that we'll then have to use to bootstrap the physics notion of time and space. So what I will do is show you a dynamics on an abstract consciousness space, and from that I will give you Minkowski space-time, which will also bring in the time. Yes?
Where is mathematics in this?
Where's mathematics?
Yeah.
In what sense? What's the
Well,
ontological status?
Conscious is primitive, right?
Yes. So
it's mathematics.
Yeah.
It's not a species-specific interface.
Well, what I'm thinking, of course, that's a very, very deep question, and Penny, Maddie, and others spend their entire careers worrying exactly about that question. So I'm not going to give you one line that's going to take care of it, but the way I'm thinking about it is that that mathematics is part of the structure of conscious agents and their contents, so that it's an integral part of the whole structure of conscious agents and conscious observers. But I would absolutely agree that you're pointing to some very deep issues. No doubt. So let's take, for concreteness, a 1D case. Here is a line. Each point on the line represents a conscious observer, because the states are conscious observers. And here's two agents, agent 1 and agent 2. They're dynamical agents governed by Markovian kernels. And let's assume that they observe each other, and all they can get is direction, but not distance. So agent 2 can tell that agent 1 is to its left, but that's all it can tell. It can't tell how far. And agent 1 can tell that agent 2 is to his right, but can't tell how far. And they can change, they can look. So here's the sort of the discrete time of my dynamics. The discrete time is an individual act of observation. You get a particular bit of information, left or right, and then you get a chance to change your state, to change which observer you are on the state space, and then look again. Okay, that's the dynamics. two possibilities. You can approach. Suppose your strategy is every time I look, if the guy's to my left, I move to my left. If he's to my right, I move to my right. So the guys are going to keep approaching. If they cross, they'll go the other way, and they'll keep going back and forth like this, right? They'll be, if your rule is always approach with some step size, always approach the guy, then you will eventually end up with a stable dynamics. There'll be some stable distribution of the relative positions of the two agents. If, on the other hand, your approach is to always depart, so every time you look at the guy, if he's to my left, I move to the right. And if both guys do that, there's no stable dynamics, right? There's no, but here's what I mean precisely by no stable dynamics. There's no invariant probability measure that describes the asymptotic behavior of the dynamics. There's no probability measure that describes the asymptotic behavior if they always depart from each other. But if they always approach each other, then there is a probability measure which describes probabilistically the distribution of their relative positions on the space with respect to each other. And notice what that allows. Right now, before they move, their uncertainty about the position of the other is infinite. It could be anywhere on the line. They have infinite perceptual uncertainty. If you engage in this approach strategy, then you can change that uncertainty from infinite to a very finite amount, the variance of this invariant distribution. So the possibility of perception depends entirely on which actions you take. So there's this very tight perception-action loop in the 1D case. So we can imagine, for example, to be concrete, that each agent takes a step according to a Gaussian distribution whose mean mu is in the direction of the other agent, and there's some variance to it. And then maybe agent 1 moves to step x1, position x1, and agent 2 moves to position x2. And so if their initial distance was r, we can ask what's the probability that if they were r apart to begin with, that they'll be q apart afterwards. We can actually write down a Markov chain. And when we do this, we can actually write down the transition probability for this particular dynamics that I showed you. Here's the transition probability for it. This is a graphical representation of that transition probability. R is the initial distance, Q is the distance after one step. And I'm collaborating with John Merzel and Fat Vu. We're working to get the eigenfunctions of this and classify the asymptotic behaviors. By looking at the eigenfunctions, we can get the asymptotic behaviors and the invariant distributions and so forth, standard Markov stuff. That's the 1D case. I only looked at 2 agents there. If you have more than 2 agents, you have a question of who's looking at whom, right? Right. This gets very interesting. So the rules will be, we'll go into this in great detail, but the rules will be that if there are a bunch of agents out there and I'm an agent and I'm trying to decide who to look at, the closer another agent is to me in some metric on the space, the more likely I am to look at that agent. Makes sense. So the nearer in the metric, the more likely I am to look at that agent. And second, the farther away the nearest agent is to me, the more likely it is that I won't look at all at anybody in this step of the dynamics. So there's a probability that at this step of the dynamics I won't look at all at anybody. And that's going to depend on how far away everybody is from me. Those basically are the 2 key ideas behind the probabilities of looking at multiple agents.
So,
yes?
There's no assumption of dependence or anything?
In what kind of dependence do you have in mind?
Well, maybe if you have several agents and...
If A looks at B, does B look at A?
Yeah.
Yeah, no assumption of that. It's interesting, Bruce, the gentleman I collaborated with for many years, wanted to have that kind of dependence, and maybe he's right. Right now I'm thinking about it as no dependence. Bruce wanted it to be a binary relationship. If A looks at B, B has to look at A. It's more general to relax that constraint, so I'm trying to look at a more general approach. I think Bruce's idea is more restrictive than what I want. So right now, A could look at B, B could look at C, C could look at nobody. Now let's move to the 2-dimensional case. We're building up intuition. So in the 1D case, we found you could approach, then you have a stable dynamics, and you have perception that has got less uncertainty. And if you departed, then there was no possibility of perception. in the two-dimensional case, a little bit more complicated. This agent, let me go. This agent A1 could approach A2 in a lot of different directions, right? There's a whole hemisphere of directions that are, in some sense, approaching. So it turns out if A1 takes a step in this half plane, on average, and A2 does the same, then there will again be no stable dynamics. They'll depart from each other and there'll be no invariant measure to describe their dynamics. But if both of them step at some angle toward each other, somewhere between 0 and 90 degrees, then there will be a stable dynamics. Okay. So it's a little more complicated in the 1D case. So what we do is in our dynamics, we assume that we now look at the previous step vector of each agent. And then we assume that, again, there's some Gaussian or other kind of probability that governs the step. I've indicated maybe here's the mean of the Gaussian. It's roughly some length L from your current location. And it's at some angle alpha 1, alpha 2 from your current, with respect to the direction vector between the two guys. And this probability measure, so Gaussian here and Gaussian centered here, governs the next steps that the agents will take. So in this diagram, agent 1 moved from there to there, and agent 2 moved from there to there. So their initial distance vector was r, and after they take a step, now their direction vector is q. And you can again build Markovian dynamics of the agents. And it's going to be stable if the angle alpha here is less than 90 degrees. You can write down the transition probabilities and analyze it. There are two kinds of dynamics. If the two agents move toward each other in this way, so here's agent 1 and agent 2, they're going to scissor across each other and keep going in a straight line. Whereas if they approach each other like this, here's agent 1 taking a step toward agent 2 that way, and agent 2 step that way toward agent 1, they'll go in a circle. When you actually look at the dynamics, you get two different kinds of behavior. One in which they have a stable dynamics, but the pair is translating rapidly through the space. And another in which they start off here and then they end up cycling. So the green is one agent, the red is another agent. They end up cycling in some asymptotic behavior. Now we go to 3D. Now, so here's agent 1, agent 2. Use the directed vector between the two. And now you have, if you have some angle alpha of approach, there's a whole cone of directions you could step. So what we assume is that there's a minimum action principle. Each agent, if his last vector was v, and the distance to the next guy is d, as vector, then needs to define a plane, and O is the perpendicular to that plane. We call that the action plane. And this agent will take a step at an angle alpha in that plane. So the step is of length w, and it lies at an angle alpha in the plane perpendicular to O. We also assume that it steps in a direction such that this vector w has positive dot product with v, not negative dot product. So it's sort of a minimum action principle. So we can characterize this agent's possible steps, with a complex number, a single complex number. Right? Complex number has an angle and a length. The angle of the complex number would represent the possible 360 degrees that O could be rotated. And the length is the length W of the actual step. So we can use a single complex number to characterize much of the dynamics of this agent, and another complex number to represent the dynamics of this guy. Okay? The angle of the action plane and the length of the step vector. When we actually put these guys into dynamics, we get these kinds of results. Here, the green is one agent, the red is another. They will spin around, but now if the action planes aren't coplanar, if the action planes of these two guys, so if this guy's action plane is not coplanar to that guy's action plane, then you're going to have some torsion. They're going to be twisting around and performing double helixes, basically. And that's what we see here. They do these double helical motions. So they'll be translating through space, but they'll have some asymptotic distance that they maintain. That's a stereo pair, by the way, so if you can free fuse and actually see it in 3D. And here I've run some simulations in Mathematica. I send two agents here. The yellow and green are 2 different agents. I arranged them so that they're heading toward these 2 agents. I stopped the simulation here. Then I continued it, and what happens is they collide, and the 4 agents actually form a new unit and take off. Instead of doing this circular kind of action, they're doing the scissoring, where they just take off very, very quickly. Very reminiscent of changing from mass to light. And here's a simulation where I just threw down 8 agents at random with random initial vectors, and to see what would happen. They started off in the middle, and what happened in this case was pairs took off and did their helical thing and took off. And I've done agent dynamics in 4 dimensions, and you can do projections onto various 3-dimensional subspaces and get different results as well. So we're looking at simulations in more dimensions. But I want to move on now to how this ties into physics. I have a 5th postulate, what I'll call the unity postulate. And that is that when we have pairs of agents or more agents that are engaged in a stable dynamics, like the helices that I was just talking about, they actually create a new unified consciousness. So that's another postulate about how consciousness works. Okay? Stable dynamics actually creates a new unified consciousness. One intuitive way to think about it is, in our own personal experience, the 2 hemispheres of the brain. If you cut the corpus callosum, there's all sorts of empirical evidence suggesting that you get 2 separate spheres of consciousness. You can get a person who picks up a key with her left hand and a ring with her right hand and so forth, and gives evidence of disunified consciousness. But when the corpus callosum is intact, as with most of us, we have this experience of a unified consciousness. 2 separate consciousnesses in a stable relationship end up giving us a single unified consciousness. So I'm going to postulate that as a general property of consciousness, that when conscious agents are in a stable dynamics, there's actually a new unified consciousness that comes out. And this will have mathematical repercussions. When I look at the symmetry groups, the possible stabilities of this dynamics, I could use a single complex number to represent this guy's action plane and step size. I could use another complex number to represent this guy's action plane, orientation, and step size. And you can say, well, what is the symmetry group of possible dynamics of this? Well, you could say, well, it's just all possible rotations of this angle and lengthening or shortening of W, and the same thing over here, and then possibly I could swap these 2. If I just did a permutation of these 2 guys, that would also leave the dynamics invariant. But if you actually take this unity hypothesis postulate that I just gave, that when you actually have 2 agents in stable dynamics, you get a unified consciousness, then the symmetry group is much deeper. So the symmetry group will actually be SL2C. SL2C. So here's the 2 complex numbers. SL2C is the set of all 2x2 matrices with complex entries and determinant 1. And what does it mean to say that SL2C, this matrix A, is what transforms the action plane and step size of the first agent, action plane and step size of the second agent, into a new dynamics over here? What does it mean? Well, well, first here's how we do it. We let the angle of C be the action plane angle for the first agent, and the absolute value of C be the step length of the first agent. And then there's a little trick, I have to take eta inverse and take the arc of it to be the action plane angle of the second agent, and the absolute of the inverse for the step length. A little trick there. But when we do that, what we're saying is, not only are we rotating each agent's action plane separately and permuting them, we're also looking at all possible, essentially, complex superpositions of the 2. The fact that we can take all possible, what SL2C is doing, what A is doing here, to go from C and eta to C bar and eta bar, or tilde, is doing a complete mixing, linear combinations of them. So the linear superpositions are the mathematical signature of the new unity of consciousness. That's the idea. So that's why it's SL2C. All the superpositions, the linear superpositions in SL2C, are the mathematical signature of a new unified consciousness that's coming up. So it's a deeper symmetry. You get a deeper and richer symmetry as a model of the new unity of consciousness that comes up. So once we have SL2C, we can now, what I'm about to tell you is standard stuff. For example, Roger Penrose's book on spinors and spacetime has this stuff. Once we have C and eta, the two complex numbers which represent our dynamics of our agents, we can canonically view them as points on a Argand plane and back project them onto a Riemann sphere. This is now just standard complex analysis. And we can view that sphere as the intersection of, this is now Minkowski space, where T is the time axis and we have a space axis. And we're taking, this is the light cone. And we're taking a section of plane T equals 1, time equals 1, with the light cone, and we get the formula x squared plus y squared plus z squared equals 1, namely a sphere. So this is how we get that sphere. We think of that sphere as the intersection of the null cone of Minkowski space with a particular time slice. That allows us, this is just a representation of Minkowski space. And this dynamic graphic just shows you what happens when you do various Lorentz boosts, when you change your inertial frame, and how the coordinate systems change. But the key thing in Minkowski space is it's a four-dimensional space-time, time and three space coordinates, where the inner product is of this form, t squared minus x squared, y squared, z squared. So this is the space-time of special relativity. And we can then, using the mathematical framework I just described, it allows us to convert from C and eta, which are the complex representations of our agents and their dynamics. These formulas convert to T, X, Y, and Z of Minkowski space. In other words, given a stable dynamics of two agents of the type I just described in 3D, their symmetry group is SL2C. There is then a canonical way to associate to that pair of agents a little patch of Minkowski space. Here it is. This is the formula. So for every pair of agents, we get to associate canonically a little piece of relativistic spacetime, a little piece of Minkowski space. Remember that the spin matrix A had entries alpha, beta, gamma, and delta. That was how I'm mixing the conscious agents. So here are the alpha, beta, gamma, and delta, and the bars are their complex conjugates. This matrix B is a 4x4 matrix which performs the Lorentz transformation. So this, if you want to take Minkowski coordinates Tx, y, z, and map them to, under a Lorentz invariant way, to T prime or T tilde through Z tilde. This is the formula that does it. It gives you a Lorentz transformation in terms of the parameters of our dynamics of conscious agents. So this is, it's nasty, but it's explicit about how you go from the representation of the symmetry of the conscious agents to an explicit Lorentz transformation in the new space-time that you get. Here's a theorem. This is not my theorem. It's a standard theorem in the field. Every spin transformation, namely matrix A that I mentioned, corresponds to a unique restricted Lorentz transformation, and conversely, every restricted Lorentz transformation corresponds to two spin transformations, one being the negative of the other. And this is the correspondence. So you go from one set of Lorentz coordinates or Minkowski coordinates to another by this action of that matrix A. And if you take the negative of A, you get the same action as if you take the original A. That's why there's this dual relationship. And spin theorem 2, every unitary transformation, spin transformation corresponds to a proper rotation of that Riemann sphere S+. So it's just a pure rotation. And again, this is This is the transformation it does. This is for the SL2C as a subgroup of unitary spin transformations, which just rotate coordinates but do not do Lorentz boosts, that do not change their inertial frame. And this is the matrix representation of that transforms the spin coordinates of the agents into new spin coordinates, but doesn't do a boost. This is the spin transformation that does the boost. So you just have alpha b w to the half and delta b w to the minus 1/2. This w turns out to be, in relativity theory, it's called the relativistic Doppler factor. And its log is the so-called rapidity. And the hyperbolic tangent of that is the standard velocity in relativity theory. There's also an internal spin effect in this SL2C, which has no effect on the Minkowski coordinates. So if you transform the action plane and step size of that agent and that agent by this transformation, r e to the I theta, r e I to theta, you will not, when you look at the formulas I gave you for the conversion into Minkowski space, the formulas for the Minkowski space are invariant under this entire set of possible transformations. This is a hidden set of transformations that you can't see in the physics. But this is the source of the spin half property of the particle. And in fact, I'll just show you temporarily. Okay, this I'll do here. Here I've got a little applet I created to show you this effect. So think of the green disk and the red disk as two conscious agents, and the two little arrows, the vectors here, as their action planes. And I'm keeping their step size constant for current purposes. And notice what happens. I can start them off at about a 45-degree angle off to the right, and I can rotate their action planes so that, notice the red and the green have both rotated 180 degrees, right? So the angle between the two action planes has actually rotated 360 degrees, right? But when I rotate 360 degrees, I don't get back to my original thing. I'm actually at minus my original state. It's only when I've actually rotated another 360 degrees that I get back to the original state. So you have to rotate through the angle between the action planes has to rotate 720 degrees before you get back to the original state. That's exactly the property that spin half particles have. So if you read in standard physics, they say an electron is this funny little particle. It's a point particle. You rotate it 360 degrees, you don't get back to where you started. You have to rotate it 720 degrees to get back where you started. Here's why. So the rotation I just showed you graphically is this internal spin rotation. And it's the source of the 4-pi symmetry as opposed to 2-pi symmetry that characterizes spin half particles. So now, tying this in, so what I'll say right now is the following. We have a way of coming up with the dynamics of conscious agents, canonically associating to every pair of conscious agents a piece of Minkowski space. Now, in standard general relativity, space-time is curved. It's a curved manifold. And at every point of the manifold, you have a tangent space. And that tangent space is a copy of Minkowski space. So you have Minkowski tangent space at every point. So what I'm getting in this dynamics is a bunch of discrete pieces of Minkowski space at different places in this consciousness space. We can now imagine trying to take all these little bits of Minkowski space and piece them together with some kind of smooth approximating function to give us roughly a smooth space-time out of it. That's the approach that we're working on to try to get general relativity coming out of this. Now, right now, in theoretical physics, they're working on, of course, the big quest to its theory of everything to unify quantum mechanics and general relativity. The two big contenders are string theory and loop quantum gravity. Lee Smolin is one of the big proponents of loop quantum gravity, but both camps agree that the solution is going to require that we discretize space and time. The way to unify quantum mechanics and general relativity, we're going to have to give up the notion first that space and time are the framework in which things occur. They can no longer be the framework in which things occur. We have to create space and time out of this new theory of everything. And moreover, space and time will have to be discrete. And there are theorems, actually, studies in black holes and the Bekenstein theorem about the entropy of black holes that indicate that even if loop quantum gravity is wrong and string theory is wrong, it's still the case that space-time is discrete. It's pixelized. Yes?
Discrete, I can see, but discrete, finite, that's kind of tough. It says which can be counted.
Yes. Now this, of course, this is not me. This is not my claim. This is Lee Smolin. This is what the loop quantum gravity people are saying. The idea, yeah, that there's a discrete, well, which can be, they could be countably infinite. So I think he's talking about, this is a book for popular audience. He's probably talking countable infinity. So we're still dealing with infinities, but just not continuous infinities, discrete infinities. And that would be fine in my approach too. There could be literally a countable set of conscious agents in various kinds of dynamic world. So I would have, again, this kind of thing. So what the physicists are saying is, the apparent smoothness in space and time are illusions. Behind them is a world composed of discrete events which can be counted. They're trying to figure out what those events are. What is the nature? What ontology do we need to propose to get a discrete space-time emerging? Now, I would actually, of course, predict from my point of view that space and time are pixelized because they are just the user interface. If you look real close at your user interface on your computer screen, you see pixels. And so space and time are just the species-specific user interface, and they're pixelized when we get at the smallest levels. No surprise. This is a big hint to us that space-time and physics in general is not the fundamental framework. It's a species-specific, dumbed-down set of symbols. We have to think outside the user interface box to get somewhere. And the opposing view in approaches to quantum gravity is Brian Greene and others of his ilk that do string theory. And Greene also concludes that, he says in his recent book, The Fabric of the Cosmos, that space, like electrons, comes in discrete, indivisible chunks. Space and time are pixelized. We need that to get our ultimate theory of space and time. And the very fabric of space and time is composed of more fundamental spaceless and timeless entities. But he doesn't know what they are. I have a proposal. Those spaceless and timeless entities that they're looking for are in fact conscious agents. And the stable dynamics of those conscious agents actually leads to the bits of Minkowski space we need to piece together to get the unified theory they're looking for. So just to summarize, the idea then is the physicalist approach in science has worked fantastically since Newton and made great successes. It's running up against two big problems today. One is the mind-body problem, in which it's completely powerless so far to give us any good theories. And number two, it's running up against problems in the construction of a theory of everything. These theories can't bring in consciousness. They don't have any consciousness. They're theories of everything, but they leave out the only thing that's really important in some sense, which is consciousness. So these two problems with the current physicalist approach, I suggest, are indications that it's time to look for a different framework. And we can do this in a mathematically rigorous fashion. We can have a completely axiomatic and mathematically precise approach to science based on the ontology of conscious realism, where consciousness is fundamental. And we can go about systematically showing how the physical world and all of current physics is mathematically derived from that framework. And that's the goal of the projects we're working on. So, yeah, we stop around time, we can have questions. Everybody buys it?
there predictions of empirical observations that arise
Yes.
that haven't previously arisen? And the second question is, I saw a report recently about a clinical case. They were going to do an epilepsy operation, and they moved electrons around to find where they ought to cut. And in the process, they found some strange subjective experiences on the part of the subject, namely out-of-body experience. And I'd like to see those two
Discussed in this room. Yes, okay. Of course, your first question about empirical predictions, that's absolutely where we need to go. Our hope is that because we have a Markovian dynamics whose asymptotic behavior we're going to tie in with quantum theory, that we'll actually have a richer dynamical framework than the quantum theory, and we can make new predictions. That's our goal. But we do have a framework in which weirdness of quantum mechanics, like entanglement and non-locality, can be approached. Right? If you think that space and time are fundamental, then it's very, very strange that two entangled electrons can be a billion light years apart, and you measure the spin of one, the spin of another a billion light years apart is immediately collapsed. That's very, very strange if space and time are the framework in which everything's happening. It strongly suggests that they're not the framework in which everything's happening. And that fits very, very well with the kind of framework that we're doing. It is, in fact, my goal to get empirical predictions, but not easy. Second, about the brain experiments. There are, of course, thousands of correlations between brain stimulation, brain damage, and so forth, and conscious experiences. And so there's thousands of neural correlates of consciousness. They're typically interpreted as evidence that the brain causes consciousness. And, of course, that's a good direction to look. The problem is that we've not been able to come up with a single theory about how that could be. So we have all these correlations. We think the brain causes consciousness, and we're clueless, as Colin again pointed out. We're clueless to get a theory about how that could be. So I am saying that those correlations can have the different direction of causation. Consciousness causes the physical world in the manner that I've described. In a particular, consciousness creates all the objects we see around us, including the brain. Now there's a radical implication of this. The brain has no causal powers. Right? If it's just a symbol created by a conscious agent, then the brain itself, although there are all these neural correlates of consciousness, they don't indicate that the brain has the causal powers. It's rather that consciousness is creating the symbol that we call the brain as it interacts with other conscious agents. So it's a dumbed-down user interface symbol to represent a very complicated interaction between conscious agents, and we have to reinterpret it in that framework. But right now we're stuck trying to think that the brain has causal powers and creating consciousness, and we're getting nowhere.
I don't think it's a point.
Okay.
The person getting the electric stimulation is feeling out-of-body experiences, but none of the observers in the operating room see such a thing going on. So
Yes.
it's quite there's inconsistency among observers.
Oh, so you're asking about inconsistency among observers.
Part of it.
Well, we could certainly have that happen, right? Because within this framework, there are no public objects. So, for example, when you look at the table, according to conscious realism, there are as many tables there as there are people in this room creating the table symbol. So if the way you create symbols slightly deviates from the way I create mine, you could have a conscious realm of experience that's very, very different from that. So that's the kind of thing that's very easy to understand within this framework, actually. Yes.
So a skeptic might say that you could do what you did without even invoking the term consciousness. So, for instance, Holman got his theorem without thinking about it in that way. So,
Yes.
in what way would you rope off something about what you're talking about? It's clearly of the character of consciousness.
So you could. That's right. So the math itself, the word consciousness is nowhere in the math. Right? It's just math. The reason I'm talking about consciousness is because I'm interested in the mind-body problem. And I want to understand how consciousness is related to the physical realm. And so I have to talk about consciousness to deal with that. The mathematics, of course, doesn't dictate an interpretation in terms of consciousness. But then that's true also if you look at the Schrodinger equation for the free electron. Mathematics doesn't dictate that you interpret it as the equation of the free electron. So the problem is not unique to my situation, it's ubiquitous in mathematics. The mathematics is mathematics, and our application to particular content areas is up to us. So the way I would look at it is it's rather interesting that when I use the mathematics in this content area, I actually get SL2C, I get the connections that I would need to make to try to get physics coming out of this.